Ah, under the hood. I loved it when I found this illustration on the internet. That's exactly what I feel like. We're diving into this thing, and I got to watch out. I'm going to fall in and get totally lost. So we'll do the best we can. If you have a question, let's do this. Please stop, interrupt, unmute, and call out the question. If we wait till the end, you kind of lose the liveliness of the talk, and you'll probably forget the question anyway. So if you have a question, just I'm not watching you all. Raising your hand in the window won't help me because I can't see everybody. All right, so we need to talk about Smith charts. Why? Well, they're just so cool. I realized looking at this, that could be intimidating, right? You know, all these numbers, and there's nothing X's and Y's anymore. So let's take a look at Smith charts. So a Smith chart is just simply a plot of two things, resistance and reactance. So we better know what those two words mean, right? So we're used to thinking of resistance, you know, ohms. So I gave a talk at a local radio club, and I said, let's start from basics. Give me a description of the word resistance, but in words. I don't want Ohm's law formula. What is resistance? And like 20 minutes later, we were still arguing, oh, what is resistance? And they said to me, well, how do you think of it? I think of it like obstructions. When I taught physics to a bunch of students in college that were going to be elementary school teachers, I put the desks together in different ways, and I lined them all up, and I said, you have to run and get either under or over every desk in the room. So that was quite a challenge because they'd have to crawl under a desk, get up, run, jump over. You know, they were obstructions, just like hurdles. And I said, that's the way I think of resistance in a conductor. These little things called electrons are trying to squeeze through and avoid hitting the atoms, but they can't. The atoms are in their way. So electrons keep colliding with atoms. The electrons bounce back. The atoms might vibrate and get warm. So resistance results in heat. So that's the way I think of resistance. So with an antenna, we can't quite think of it that way, can we? What is resistance in an antenna? Well, you might say the feed line comes up, and if you put a voltage across the feed line, you get some kind of current. So if you just take the ratio of the voltage to the current at the feed line, that's the resistance. So it's kind of a practical definition of the word. Okay, so what is reactance? That's a little more sophisticated, isn't it? So reactance is sort of what happens with reactance-type objects like coils, capacitors. So there you have a timing issue, a phasing issue. So we'll come back to understanding reactance. But in an antenna, I think of reactance as just the voltage and current are getting out of phase. Use that as the analogy. So if I make a plot of over here, can you see my cursor, I hope? If you see J, the vertical, that's representing reactance. It can be positive or negative, meaning what a capacitor does or what an inductor does. They change the way the voltage and current align with each other. But the horizontal axis is our familiar resistance. 0 here is 0 reactance, 0 resistance. All right, that makes it pretty easy. So if I plotted a graph of reactance, everyone would see, oh, yeah, that makes sense. I get it. So why did Smith create this Smith chart? Well, it's very clever. So the reactance is the plot that moves around so that it gradually curves to the point where you have a polar graph system, a polar system. So now we're talking about what's in the center and what are these different lines and curves represent on a Smith chart. So that's what I'm going to take a couple minutes to derive. So fundamentally, this horizontal bar still represents resistance. And I'll show you this in some expanded graphs. And as you go up and around clockwise or counterclockwise, you get reactance. That's the timing issue. So let's start with the simple stuff. So on a Smith chart, 0 ohms plots on the far left, right over here. What do we mean by 0 ohms? Well, no resistance. Perfect conductor, right? No resistance. And a real lousy conductor, like infinite ohms, plots over here on the far right. So that's, for our purposes, hundreds of thousands of ohms. Real big. What's important for us is, well, the center I can manufacture when I do a Smith chart to be any value I choose. So when I calibrate this NanoVNA, I will often do it making 50 ohms the bullseye. Why would I want to do that? Well, it's because my radio says it has a 50 ohm output. My antenna says it's looking like 50 ohms over much of the frequency range. I buy coax and it says 50 ohm coax. I don't know what's so magic about 50, but that's what the world seems to have adopted. So I'm going to have my Smith chart be the bullseye 50 ohms to sort of go with the trend. Okay, so far? The bullseye, I'm going to make 50 ohms with my NanoVNA when I calibrate it. Now, something else. It's not a linear scale. Oh, who cares? That's important. So it goes 0 ohms, 10, then 25, 50, 100. So you see it's progressing geometrically here. So it's not a linear scale, and 50 is the bullseye. 0 is the far left, infinite, far right. Okay, so far? Question, Terry? I heard someone call out a question, but I couldn't hear who. Not sure. Okay, call out a question if you have one. So the resistance I can say is 50 ohms in the center, and anywhere along this circle would also be 50 ohms, but it would also then be some reactance value. If it's 50 and no reactance, it plots right here. If it's got inductive reactance, it's 50 plus something over here. So these are called circles of constant resistance. 0 ohms, well, that's the outside of the chart. 50 ohms, bullseye. And of course, the higher you get, the closer you are over here. The right, the circles kind of condense here. So we call these circles of constant resistance, although up here they have reactance, and down here they have reactance. Okay, with the concept of a resistance circle. Notice they're not concentric. Okay, so the reactance. This is a little trickier. So reactance is also in ohms, but it's how capacitors and inductors behave in an AC circuit. So I don't want to go too much backwards into how they behave, but if you have ever studied conductors like coils, as soon as current goes through a coil, it generates a magnetic field. That magnetic field opposes changes, and you get into some interesting things referred to as inductive reactance and inductance. Same thing with capacitors, but they behave differently. So if you have 10 ohms of reactance, that plots here, or anywhere along this curve. These are curves, not lines. 25 ohms would represent more inductive reactance, like a bigger coil. 50 ohms, 100 ohms. So as you get higher and higher values of inductance reactance, you're curving around the chart. So these are the high values over here, the low values over here. If it's a capacitive reactance, meaning it behaves more like a capacitor, 10 ohms, 25, except it's preceded with a negative sign, negative J10, negative J25. But you get the idea. So all of these, is this blue? All these blue curves represents curves of a reactance value. Notice all these curves will intersect somewhere, the resistance curves. Hence you can see every impedance has some location on this chart. So I picked a couple. Bullseye, 50 ohms, resistance, no reactance. So there's the bullseye. So remember, that's important. 50 plus J0. The J0 means no reactance. 50 is resistance. Plus bullseye, bullseye. How about 10 ohms resistance, 25 ohm reactance? So you start out with the 10 ohms, then slide up, up, up until you get to the point where this is half of 50 is 25. So 10 plus J25 would be there. 5 plus J50 way out here. I actually had some ham sticks on 80 meters that look like that. Very low resistance and a high reactance. That's hard to match the 50 ohm coax. It won't work. So how about down here? Well, it's basically the same thing except they're negative J, meaning a capacitive reactance. So fundamentally, you give me any reactance value, anything, it'll plot somewhere on here. Now it may plot way over at this end or way over at this end. They're sort of equally bad. You want to be close to the bullseye for 50 ohm radio, 50 ohm coax, 50 ohm antenna. Robert, question? I heard someone on mute. Robert? No? Okay. All right, so I'm going to keep coming back to this again and again. I want to be in the bullseye. Why? Because that's where 50 ohms is. and I'm assuming my system is kind of tuned at 50 ohms. I realize you might have a different impedance value. You run balance line or ladder line or a ZEP antenna or something, but I'm talking about kind of typical dipoles, beams designed for 50 ohms. Bullseye, bullseye, bullseye. Okay, now let's get involved with the innards of the NanoVNA. What does it actually measure and what does it compute? That's good to see the difference in those two things. So here's what it actually measures, something called a reflection coefficient. I'd never heard that term as a ham, and I've been a ham for 60 years.
No,
why did I never hear the term reflection coefficient or gamma? Question? Someone's unmuted and I keep hearing background sounds.
Dave, put yourself on mute.
All right, I'll keep going, but I'm hearing sounds in the background.
There are 3 people. Not 3 people. There's Terry. And
I think it's Robert Johnson. Oh no, he's muted now.
Yeah.
Okay.
He was.
All right, so I picked up this slide. I didn't make it. It's a gorgeous slide from Agilent Technology. They've got great web pages. I mean, they're the professionals designing and explaining it, what this is. So a reflection coefficient, what I'm talking about is the absolute value of that. So a reflection coefficient is really this thing. It's a complex impedance divided by another complex impedance. We're not going there. That's like, above 12th grade. But if you take a value and take its absolute value, you get something much simpler called the magnitude, or I'd call it the absolute magnitude of the reflection coefficient, and that's called Rho. That's easy to see. Rho is just a fraction from 0 to 1. Couldn't be any easier. It's more simple than SWR. Reflection coefficient has to do with what's coming back on the feed line from the antenna back towards the radio, or your NanoVNA, compared to what's going forward. It's just a ratio. It could be 0, could be 1, or anything in between. Now, return loss. I came across return loss and I said, I've never heard that term. Engineers use it all the time. I don't know if they're among any engineers here, but return loss is not something I've ever seen in a ham radio journal. What is it and why is it so useful? It's related to the reflection coefficient. It's far more descriptive than SWR, let me say it that way. So I'll show you what it is, how you define it, how you derive it, and why it's so useful with a couple of graphs. SWR. Well, I've heard that ever since I was a 12-year-old. I had to learn something about SWR to pass a test. I knew nothing. Standing wave ratio. Okay, I don't know what it means. I'm 12 years old. I pass all these tests. I don't know anything, but I just pass these tests because I memorize the answers to questions. Maybe that's the way a lot of people, treat all this technical stuff. Just learn the words. Learning the words doesn't mean you understand the words. It just means you memorize the words. So here we go. If your Rho is 0, what does that mean? The fraction means reflected over incident is 0. Well, that sounds pretty good. I don't want anything reflected on my antenna. So a low number is good. You can't get any lower than 0. What if reflected and the incident voltage are the same? That's 1 over 1, 1. Well, that's no good. I'm over here. That would mean, wait a minute, if I send 1 watt this way, 1 watt comes back, my antenna is rejecting everything. Oh, I know, that's no good. So I don't want a high Rho value. High means 1. I want a low Rho value. Okay. Return loss, well, it's just calculated from the reflection coefficient. Negative 20 times the log of Rho. All right, so we better talk about logarithms. And then SWR. That's a simple number from 1 to 2, 3, 5. The higher the number, the more unhappy I am. You want the SWR low because it's sort of the quality of the match. So here we go. So let's dig into this. So the reflection coefficient, Rho, Greek letter, Rho, R-H-O. It's the absolute magnitude of the ratio of the complex impedances. I don't want to deal with that. It's just a fraction. Okay. If it's 0, okay, so what does that mean? If it's 0, well, wait a minute. Nothing's reflected, right? I don't want anything reflected. I want my antenna to radiate it all. So a reflection coefficient of 0 means I think my antenna is working well. Or maybe I've got a dummy load. I don't know. But I'm happy with that. The worst would be as my reflected and the forward voltage are the same. Oh, yikes. That means the ratio is 1. So 1 means all the energy is reflected. Antenna shouldn't do that. Should radiate, not reflect. Okay, with this definition, reflection coefficient. That's easy to see. Return loss. Oh, okay. So I've had some arguments with engineers. So return loss is first, it's a log of a ratio. All right, well, what does that mean? So rho is a ratio, right? So I'm taking the log of a ratio. So now I can convert it to something that I like, a decibel. Why do I like it? Because there's so many things measured in dB, decibels. Why negative 20? Oh, well, that's kind of interesting. Why negative? Oh, because a return, you want to be what? A big number or a small number? You have to think about that. I don't want anything returned. I want it radiated. So if whatever comes back, I want it to be what?
Small as possible.
Yeah. So return loss. Well, let's see here. If the return is small, see, once I say the word loss, it gives it away. I don't want anything coming back. I want the return signal to be nothing. So I want the return loss to be big. It's like the reverse logic. I'll come back to that. If we didn't have the word loss, I think it would be fine. We'd all understand it. I want the return loss to be a big number. I want the return to be a small number. It's like saying, going to the bank, my balance is negative 200. I'm in trouble. So engineers write this as a positive number. So it's a negative 20 times the log of rho. Well, the log of a number between 0 and 1, that's a negative number. A negative times a negative, so this is technically a positive quantity. I often think about it as negative, and the engineers tell me, Barry, get over it. That's wrong. So if it's 1 plus rho over 1 minus rho, the SWR, so let's check that out. What if rho is 0? I'm happy. That's good. If rho is 0, I've got 1 plus 0, that's 1, over 1 minus 0. Well, that's 1. 1 over 1 is 1. Oh, that means the ratio of the maximum to minimum voltage, which is the way I think of SWR, is 1. Oh, is that good? Yeah. So wait a minute. Let's see here. If rho is 0, the SWR is 1. It can't get better than 1. Someone said, don't you want it to be 0 or a half? No. That's impossible. If rho is 1, I've got 1 plus 1, that's 2, over 1 minus 1. Wait a minute, that's 0. Whoops. Hey, I can't have 0 in the denominator. The algebra doesn't like that. So when rho is 1, I'm in trouble. The SWR is essentially something divided by 0. That's no good. So I essentially want my return loss, now watch out, to be a big positive number. Let me stop. It took me a month to think that through. I kept thinking, no. I want my return loss to be small. No, I want my return loss to be big. Is that okay? We may have to come back to that. It's sort of like the flip of my logic. Okay, so here's some examples. If the SWR is 1, can't get better than that, the reflection coefficient is 0. All right, I know that. How about, I often get a SWR of 2 on my antennas, and my radios work fine. I can work the world. 2 SWR corresponds to a rho reflection coefficient of about 1/3. All right, wait a minute. That means I'm sending 1 volt to the antenna and 0.33 volts comes back. That sounds kind of high, doesn't it? But my antenna works fine with an SWR of 2 to 1, most of the time. How about 3 to 1? That's where I start to see sometimes my radio's not happy. The radio starts to buzz or say something, and the power cuts back. So an SWR of 3, it's not awful, but it means the reflection coefficient, a half. I send 1 volt, a half a volt comes back. Well, let's see, half a volt would be what? 0.5 squared, a quarter of the power. That doesn't sound very good to me. And the radio starts to balk, usually, my radios, if the SWR is 3 or greater. So the higher the SWR, the more I'm going to have to figure out, I got to fix this. Maybe my NanoVNA can tell me how to fix it. So I just did this afternoon. I thought I need some examples. So in my backyard, I have a home-built 80-meter vertical. It's a very nice antenna. It's one of my favorites because it's a vertical that's about 50 feet tall, literally lashed to the tree. It's at the base about 2 inches aluminum tubing, and the sections go together. It's an old military mast. made out of good quality aluminum, and I think it cost me 10 bucks. But I literally have it wrapped to the tree with some rope. So it's touching a live tree. People say you shouldn't do that, but I did it. The base is about 10 feet off the ground, and then I have 2 wire radials going out. So it's, picture the letter T upside down. That's my antenna. So I'm using my NanoVNA to check the S11 signal. Remember, what's S11? That's the reflection coefficient. And here it is from 80 meters, from 3.5 megahertz to 4 megahertz. So here's the 80 meter band. And look, the reflection is about 29%, about 2% down here. And even at the top of the band, it's only about 30%. In other words, the SWR across the whole antenna is less than 2 to 1. That's nearly impossible to make. Yeah, I made it, and it's fed with about 150 feet of real good quality coax. I can use this anywhere on the 80 meter band. How did I get such a low SWR antenna? Remember I said it's 2-inch aluminum tubing, so it's got what some people call a broadband tuning because it's a thick antenna. Now, that's the reflection coefficient. Here's the return loss. Oh, you see why this is a little more useful maybe than this. This is more sharply showing where my antenna seems to be producing the least amount of energy coming back towards the rig. Right about here, 3,700 kilohertz. Oh, good. I wanted it in the middle of the band. So let me stop here with this slide. And I just got this slide like 2 hours ago. Look at this. Reflection coefficient measured, return loss calculated. Now, I'm getting these plots with VNA Saver. That's a software program on Windows. I hate working with the little gadget itself. I can't see the little screens and all. But VNA Saver is a great product. Okay, on return loss. So this is kind of telling me this antenna ought to work really well on 80 meters as a vertical. And it does at night when I want a low-angle signal. I can hear the whole world on this. I actually, with an antenna tuner in my shack, can load this up on 160 meters. But that's another talk. Okay, so far. So what's the SWR like on this antenna? Whoa, look at this. The SWR is 1.5 to 1. That's fine. At the bottom of the band, drops to about 1.02 to 1, you know, almost perfect match. And even at the very top of the phone band, it's about 2 to 1. Hey, I can actually use this antenna in my shack with coax and no tuner at all. Now, granted, I have a tuner over here. In fact, I have a couple of tuners, but I don't need it for this antenna. I am so happy with this antenna. The whole antenna cost me about 20 bucks. Plus, you know, the tree's holding it up. It's like an 80-foot fir tree that's holding it up. Thank you, tree. Beautiful. So my NanoVNA sort of convinced me, hey, this is pretty good antenna. Smith chart. Whoa, now I started to dread. Oh, for the impedance first, then the Smith chart. So what's the impedance like? Well, I know I want it 50 ohms, right? Why? Because my coax is 50 ohms. Why? Because I bought it, and that's what they say. So look at this. The impedance of this across 80 meters, well, it's not constant, but look, it goes from about 56 up to 60 ohms, down to about 40 ohms, and then back up. That's kind of interesting. Why is it doing that? Well, that's another hour talk, isn't it? But I want it close to 50 ohms. Where is it 50 ohms? Oh, right in the middle of the antenna. Right in the middle of the band, I mean. Oh, perfect. I'm satisfied. I thought, oh, I lucked out. Well, I measured it carefully, you know. But I didn't put it up as a 65-foot antenna. I put it up as a 40-foot antenna. How did I get it to resonate in the middle of the 80-meter band? I added a, what? What do we call that thing at the base?
Loading coil.
I added a loading coil and also a matching coil. So the combination of the two I played with, just trial and error. In about 2 hours on a hot, sweaty day, I got this thing to just tune right up on 80 meters. I thought, oh, so cool. And I learned about matching coils and loading coils. Ah, here's my Smith chart. I want to be in the bullseye. Well, look at this. I'm not very far. Someone's unmuted. Terry? I'm hearing someone. I don't know. Where's the bullseye? Well, the bullseye is right close to marker 3. Where's marker 3? Middle of the band. Oh, I couldn't be happier. Look at this. The whole here's this circle here is at SWR 2 to 1. So essentially, the Smith chart is also showing me what? The entire this antenna covers the entire 80-meter band. That's really hard to do with wire. And it works really well. Well, at night. Smith chart. Because it's curlicuing up here, is that better than down here? No. The distance to the bullseye determines the SWR, not if I'm left or right or above or below, and I'll show you that in a minute. So, I know my SWR goes up to about 2 to 1. Well, what if it went up to 5 to 1 or 10 to 1? Should I worry? So I found this chart in one of the handbooks, and I thought, I really need to include this. So be careful what this means. Line loss in dB when matched, meaning what if you had an SWR 1 to 1? How much loss do I get in what? 100 feet of good quality RG213. RG213, I look it up, and for every 100 feet at 80 meters, the loss is less than half a decibel. So over here, 0.4 decibels. This is in dB. So I start there. So what if my SWR as measured in my shack is 2 to 1? Here's the 2 to 1, 2 to 1. Then I go over here to the left, and it says additional loss caused by the standing wave ratio. Additional loss. How much? Where's my cursor? I lost my, whoops, lost my cursor. Here it is. 1/10 of a dB. I'm not going to worry about 1/10 of a dB. I'm not even going to worry about 1 dB. You'd never detect that. So if I have an SWR 2 to 1 and my radio can load into it, fine. I don't care. What if my SWR is 5 to 1 up here? 5 to 1. Well, now that's looking a little more serious. Well, then my loss is only half a dB. I'm not going to worry about that. What if my loss is, my SWR is 10 to 1? Like, that's awful. Now, I know my radio wouldn't load into it, but assume, you know, I had some antenna tuner or something. Assume my antenna could absorb that power, but the SWR is 10 to 1, so it's reflecting a lot of it. But the tuner is turning that power right back, sending it right back. So what if my SWR is 10 to 1? The additional loss from this amount of feed line, about 1.5 dB. I'm not going to even worry about that. That's a fraction of an S unit. So in other words, on 80 meters, I don't care what the SWR is, even if it's 20 to 1. The guy at the other end is never going to notice, as long as what? As long as I can fake it so my rig can deliver power to this. So on 80 meters, I'm not going to worry about SWR. How about on 10 meters? Yeah, because the losses are much higher on 10 meters. How about 2 meters? Yes, yikes, of course. How about 440? Oh, absolutely. So, but at a low frequency like 80 meters, my coax, RG213, has such a low loss, it's not worth fixing my antenna. A lot of articles in radio magazines, how to broadband 80-meter antennas. Oh, give it up. You don't have to, as long as your radio can deliver power. All right, so let's come back to the NanoVNA. You get these little gadgets with it. What are they for? They're for calibration. All right, so I'd never done this before. What do you mean, calibrate my NanoVNA? Well, it's a much more clever gadget than my crude SWR meter. It sends out a pulse of energy, and depending on what comes back, you have to look at the losses inside the machine, at the connectors on your feed line. So this is the open, the short, and the load here. They screw right on with these SMA connectors, right on your NanoVNA. So I thought, well, I'm going to do this with NanoVNA Saver. So I open NanoVNA Saver, I connect it to my computer on a COM port, and I click calibration, and here's the file that comes up. Calibration. Okay, so it wants to know what frequency do you want to calibrate. So I have to say, well, I want to calibrate it from 1 to 5 megahertz, 10 to 20, 1 to 100. I specified that in a little box. Then it says, well, how many points do you want to do? And I click on a number, and I say 2,000 points. Well, the computer doesn't care. It's got a lot of memory. So it does this. It says, all right, it coaches me. It says, put on the 0, the short, and then press this button. Okay. Put on the open and press the button. You know, connect. And I do that. And finally it says, put on the 50 ohm load and press connect. And I do that, and it says, done. And it says, now you got to save the file. So I have to decide on a name. So here's the typical names I give it. So I calibrated when I was starting here back in 9/20/20, September. So here's the calibration, 10 to 30 megahertz. Pretty small file, 167 kilobytes. Then I said, well, let's try to calibrate over a bigger range. 1 to 500 megahertz, 2 ports. It's like, whoa, watch out here. That's a lot. So that was 600 kilobyte file. And I thought, that's probably not very good, is it? I've calibrated over a huge frequency range. So I thought, well, how about just 1 to 100 megahertz? Oh, okay. Only 84 kil. So in other words, I don't care really about the size of this. But what I'm doing is calibrating this little NanoVNA over a certain frequency range. And then when I save it, I'm giving it the name of the frequency range so I know. So when I start up the NanoVNA, every time do I have to calibrate it? No, if I had to do that, I'd never use it. What you do is you load a calibration file you've already saved. Does that make sense? That's the key. So here was one I use all the time, a 2-port, 1 to 30 megahertz. 2-port so I could measure the in and the out with filters. I stopped at 30 megahertz because beyond that, I almost don't care. But I could calibrate it over 80 meters or 40 meters or 20 meters. In other words, I can make 100 different calibration files and call them each its unique name. On the NanoVNA itself, it's not that flexible. So if I calibrate right here, this becomes my calibration plane. And through poking these commands here, I can save a calibration file as file 0, 1, 2, 3, 4, and 5, or something like that. Each file, at the moment, can only save 100 points. Like, that's not many. But 100 points is okay for 80 meters, 40 meters, 20 meters, 10 meters. I wouldn't do that for 1 to 500 megahertz. That'd be useless. And I thought, okay, no, wait a minute. I'm calibrating this right here. Most of my antennas have at least 100 feet of coax out to the backyard, and then they, different antennas. What if I try this? What if I calibrate it such that I null out my coax? That's an interesting question. In other words, what if I calibrate it at the far end of my coax? Now, at the moment, I'm not going to go climb up, take my antenna down, and put the ends, But what if I just have an extra 100 feet of coax in my shack, which, of course, I do? What if I calibrate it at the end of 100 feet of RG213? So that's what I did. So at end of port 1, I think they call this channel 0, I connect here to the normal size RG213 with some, cable adapters. And at the end of 100 feet, and it's just coiled up here in my shack, I go back to the SMA, right? And then I put on the short, the open load. In other words, what am I doing here? I'm calibrating my NanoVNA at the far end of the 100 feet of coax. Why? Oh, do you see why? Does someone see why that's very useful? Whatever my NanoVNA measures, Smith chart, resistance, reactance, it's already taken into account my feed line if it's 100 feet. So what I measure on my NanoVNA is the same as if I climbed up to my antenna and hooked it right there and did the measurements, but I'm not going to do that. My other antenna analyzers aren't that smart. I thought, that's way cool. Does it make a difference? Yes, because unless my antenna is a perfect 1-to-1 match, what happens in the coax? Well, we have to look at that, don't we? So this is something to remember. If my coax feed lines were 50 feet, then I'd use 50 feet. The nice thing about 100 feet, by the way, of RG213, let's say I have 80 meters. Half-wave dipole is about 120 feet. But the velocity of RF in coax is about 70% of the velocity in free air, vacuum. 70% as fast as an RF wave in space. 70%, 0.7, 120 feet. 0.7 times 120. That's about 100. In other words, think when you buy 100 feet of 50 ohm coax, think about it this way. I'm buying a half wavelength of 80 meter coax. Is that true? Pretty close. Yeah, close enough.
Yeah.
So the other thing interesting is whatever I'm measuring, if I've got a half a wavelength of coax, then whatever I'm measuring at the VNA, the NanoVNA, is the same as if I were at the antenna. 100 feet is a magic number. I mean, it's half a wavelength on 80 meters. How about on 40 meters? It's 1 wavelength. Well, that's good too, isn't it? Man, I'm glad these manufacturers sell coax in 100-foot lengths. Do you think that's just a coincidence? Maybe. But they're selling it in multiple lengths of, 10, 20, 40, 80 meters, half wavelengths. Perfect. I thought that was kind of cool. All right, so when I do this, my zero load plots right here on my Smith chart. Zero resistance, that's the short. So when I calibrate this and bring up my Smith chart and say, okay, I put in the screw for the zero short, here's where it plots. I'm thinking, perfect. Then what's the next one? I plot in the open. So I screw in the open and my Smith chart plots it there. So in other words, I've calibrated this at some frequency. And so far so good. So I put in the load. My load, well, it says it's 50 ohms. And here's where my load plots on my Smith chart. Oh, perfect. So in other words, because my load was 50 ohms, the center of the Smith chart, I forced to be 50 ohms. That took me a while to realize. If I wanted to standardize, let's say, on 75 ohms, because all my coax and my antennas are 75 ohms, could I do that? Yeah. What do I need? Oh, I need a 75 ohm no reactance load. Oh, I don't have one. Does that make sense? Calibrating my Nano VNA as I look at the Smith chart. Okay so far?
Yeah.
So let's take a look at some yes, question.
No, just saying all good, yeah.
Okay, thank you. So what if I plug this into my coax and at the other end I have a 50 ohm load? Maybe it's a dummy load. Maybe it's my antenna. But it plots right here at one frequency. Oh, that's really cool. I can't get better than that. My antenna plots right at the bullseye. The reflection coefficient is 0. My little Nano VNA is not getting anything back, so it infers something from that. If it's not getting anything back, whatever the load is absorbing all of it. I'm hoping it radiates it, but you know, maybe it's a dummy load. Can't get better than that. 50 ohms resistance, no reactance. All right, so what if I get back 20%? How does that display on my Smith chart? Before I got one of these Nano VNAs, I couldn't tell you. I mean, I should know that, but I didn't. I thought, well, wait a minute. I know what an SWR of 2 to 1 is, and I think I know what a Smith chart is, but I can't put the two together. It plots as a circle. A circle? Wait a minute now. What's going on here? The reflection is 20%, meaning from the bullseye, 20% of the value of the radius. In other words, the radius is 1. The radius is like a row of 1. Oh, now I get it. So I want the radius to be real small. How small? Well, I'd like it to be 0. So what does this mean? Any point on the rim of this circle, any point, has a unique impedance, right? Some value of R and X. But all these points are equally distant from the bullseye, so they all have the same what? SWR. Do they all have the same impedance? No! But they have the same SWR. That took me a while to let it sink in. Does that make sense? All the points on this Smith chart, gazillion points here, they all have a different R and X value. So let me see if this makes sense. If I had 1/3, 33% coming back, my rho is 0.33 of the radius. So now my values are a bigger radius circle, right? All of the points on the rim of this circle have what? The same distance from the bullseye, which means they have the same SWR. 2 to 1. Oh, and my radio's okay with an SWR of 2 to 1 most of the time. So let me stop and ask you guys a question. I'm going to stop talking here. What do each of these R and X resistance and reactance values, what do they share in common? 25 plus J0, 100 plus J0, 40 plus J30, 40 minus J30. I'm going to stop talking, and I want you guys to talk amongst yourselves, see if you can figure this out. Anyone unmute and start the conversation. I'm not going to talk.
Silence.
They're all different, obviously. The R is different. Some are J0s, J30, you know. What can you say? They all have some value of R and X, but what do they share in common? Am I going over your heads? I expect someone to be able to say, oh, I think I know. All right.
They're all the same SWR.
Ah, okay, so you got it. Phil. So look at this. If I plot these on my circle, 25 ohms in J0 plots way over here. 50 ohms, 25. What's the ratio of 50 to 25? 2 to 1. How about 100 plus J0? That plots here. The 0 means no reactance. 50 ohms, 100. The ratio is still 2 to 1. The SWR is 2 to 1 here or here. How about 40 plus J? Well, I was a little sloppy here, but it's pretty close. 40 ohms resistance, 30 reactance plus J. Plots here, and here's 40 minus J30. They're all on the rim of the circle that has the SWR of 2 to 1. Man, if I had seen this, 50 years ago, I would have thought, this guy Smith is a genius. Look what he figured out, how to show impedance values with the same SWR. Why did I understand that? No one ever taught it to me. You guys think that's kind of cool? I'm not seeing too many nods. All right, so how about 3 to 1? Well, my radio's starting to squeak. 3 to 1, yikes. Bzz, 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 bzz. Help, help, help. So 3 to 1 means what? It means the reflection coefficient is a half. I send 1 volt to the antenna. Half a volt comes back. Well, remember, power is V squared over R, so half the voltage is 1/4 of the power. I send 100 watts to the antenna. 25 comes back. I don't know what happens to it after it comes back, but that's not good. Look what that happens. An SWR of 3 to 1. My radio is definitely not so happy. I'm not so happy. Sometimes radios shut down with an SWR 3 to 1. That's not very good. So at this point, I'm starting to think, I got to fix this. What do these RX and values all share in common? 16.7, that's an odd number, plus J0. 30 plus J40, 30 minus J40, 150 plus J0. What do these RX values share in common? And Phil can't answer. Come on, come on, come on, come on. What do these values share in common? They what?
They're all the same SWR again.
You got it. Good, thank you. So when you plot these on my crude, I kind of did this an hour ago. 50 plus J0, that's easy. That's the center. 17, well, that's 1/3 of 50, right? 16.7 or so, about 17. J0 means no reactance. So that's a ratio of 50 over 17, about 3 to 1. 150 to 50, 3 to 1. Well, they're the easy ones. 30 plus J40, that plots way over here. 30 minus J40. They're all equidistant from what? The bullseye. So what? Oh, so they all have the same SWR. Which would I prefer my radio sees? Doesn't make a difference. They're all equally bad, pretty much. Maybe my radio would rather see a resistance, no reactance, but I don't know. So do you see this? This is just, as an American expression, way cool. Awesome. So I'm getting worse and worse. Now 60% of the voltage come back 4 to 1. Radios don't like that. Oh, no, no. 90% comes back. The SWR is now 20 to 1. My rig absolutely is going to shut down. The antenna is not radiating much at all. 100% is reflected. Now that's not a dummy load. A dummy load's more likely an SWR 1 to 1. It just doesn't radiate. So what could possibly be an antenna that reflects everything? This once happened to me, inadvertently. Give me an example of an antenna that doesn't radiate anything.
One that's not connected?
Yes. So inadvertently, I put my antenna switch. See, I saw Sandra's antenna switch. I have a big one over there. And I can always blame it on my grandson who plays over there. So it was on 100 feet of coax with nothing at the end. It was an open. Oh, an open isn't a very good antenna. Well, neither is a short. So that's what this would be. You send energy down a cable and pretty close to 100% comes back. Now, granted, the cable has some attenuation. This isn't very good. All right, now it's time for a quiz. I'm a former professor, so time for a quiz, folks. So here's a Smith chart, and I've marked locations, A, B, C, D, E. My question to you, and I want you guys to unmute and talk to each other. Where is this antenna resonant? Obviously, this is a fake antenna, but that's okay. I'm stopping talking. Talk to each other. You guys are among friends. I'm not hearing any chatter yet. Come on, come on, come on. Am I still live? Or am I muted?
Yeah, no, you're still there.
I'm not going to talk. I'm going to wait you guys out. Take a chance. Maybe the answer is at no frequency. I don't know. Where's the antenna resonant? What do I mean by resonant? Your choices are A, B, C, D, E.
It's resonant in
C
D.
is going to be the closest.
I heard two voices at once. I heard one value for C. Was that David? One value for C. Phil or Barry? Someone said something else.
I'm gonna say D because it's on the center line.
D. So let's go back. What is meant by resonant? What does that word mean? Resonant.
Most efficient.
Might be. That's not its definition, though. It could be.
Outer reflected power is the most efficient.
It could be, but that's not what the word resonant means. Resonant strictly means no reactance. The voltage and current are in phase at the feed line. No reactance. Where on this Smith chart are there points that have zero reactance value?
B and D.
B and D. So the antenna is resonant. As I'm measuring it here, this might be in my shack. And this is a fake antenna anyway. So at B and D, there's no reactance. It's pure resistance. Now, be careful, because I think some of you were thinking of a different question. The answer to this is B, B, like Baker and dog. Where's the SWR lowest?
WC.
And why? How come?
Because it's closest to 50 ohms.
Closest to the bullseye. Everyone agree?
Yeah.
Yeah? Okay. I agree. The bullseye, I'm assuming now, the bullseye is 50 ohms, and this is typical antenna with 50 ohm coax. Where is the SWR lowest? At A, B, C, or D? My drawing's a little crude, but I'm trying to illustrate this. Where's the lowest SWR?
That's the same, all of them.
Who said that? Phil?
Me, yeah.
And the reason is?
Not entirely sure.
Yeah, I know, but take a guess, because your logic's good.
Yeah. Well, because they're sort of equidistant.
You got it. They're all on the circumference of a circle.
Yeah.
Of the same radius. Well, I tried to make it that way. So how about if your answer is, they look all the same because they're equidistant from the bullseye, which I have measured here at 50 ohms. Very good?
Yep.
All right, where's the resistance the least and greatest? The resistance. Not as many volunteers here.
Right.
See, I'm used to teaching ninth graders. They'd be shouting by now.
I'll say if you.
It's A again.
But yeah, it's least at A.
The least resistance. So I want to be where? Where on the Smith chart? A resistance is low?
Going towards zero.
Towards the left.
Over there. So this is kind of crude, but it looks like A and D are pretty close to the same, right? So the least resistance is probably A and D. Where's the greatest resistance?
B and C.
B and C. They're over here. How about the reactance? Where's the reactance the least?
A.
A. And?
A and D again.
I suppose.
Yeah, I didn't draw this as well as I should have. So
Yeah, all right.
there are low reactance here. 1, 2.5. 1, 2. Yeah, this is. It would probably be A, but I should have put D over here. Where's the reactance the greatest?
B and C.
B and C again. All right, so you get the idea here. So in other words, a Smith chart's pretty useful if you can interpret it. All right, so let's come back to a real basic question. Does the SWR on a feed line change along the feed line? does the impedance change along a feed line? Let's take the first one. How about SWR? Typical HF antenna, does the SWR change along a feed line?
Yes.
Yeah, because, well, part of the radiating system.
So I hear two values of yes. I mean small changes. I'm not saying add 1,000 feet of coax. How about the impedance? Does the impedance change? If you could put in a little gadget and it measures the impedance, and I measure it here and here and here and here, does the impedance change along a feed line?
It shouldn't.
Depends on the feed line.
Oh, typical 50 ohm feed line and typical 80 meter antenna. Nothing special here. Will the impedance change along a feed line? Let's assume it's not a 1-to-1. It's not a dummy load. Maybe the SWR is 2-to-1. An average 80 meter dipole. Does the impedance change along the feed line? If I move my NanoVNA 10 feet closer, 10 feet closer, do I get a different impedance at each place I measure? The answer is either yes or no.
No.
Shouldn't, no.
All right, so this is good. So I've got out in my backyard a 10 meter vertical antenna, so I'm going to pick that because it's easy to illustrate. A 10 meter vertical, I didn't make it. It's a commercial antenna. I feed it with 100 feet of RG213, real good quality, 50 ohm feed line. Here's my Smith chart over the 10 meter band, 28 to 29 megahertz. Position 1, that's not in the bullseye, but not too bad. SWR is about 1.5 to 1. Here it is as an SWR graph, right here. SWR about 1.5 to 1. Position 2, 28.2 megahertz. That's over here. SWR 1.3 to 1. Position 3, well, that's real close to the bullseye. That's down here. SWR about 1.1 to 1. Not getting much better than that. All the way out to 29 megahertz, where even out at 29 megahertz, that's up here, the SWR is only 2 to 1. So in other words, this is a commercially made antenna. I feed it with 100 feet of coax. I can operate it on the whole 10 meter band without any antenna tuner. It's fine. Works great. And it does work great, by the way. And it is my antenna. Here's my question. You ready? Now think about this. This is the key to the whole talk. What if I add 6 feet more coax? Now I'm going to add it in my shack. I'm not going to go climb up my antenna. I add 6 more feet. In other words, I take the connector off, put on a female barrel connector, make 6 feet more of coax, and attach my NanoVNA. So I've just added 6 feet. Will the impedance change? Why or why not? Will the SWR change? Why or why not? You guys talk.
The impedance shouldn't change. The SWR might.
Can you explain your answers?
Because the coax is 50 ohm feed, and the barrel connector should be 50 ohms, but the electrical length has changed, so the SWR has altered slightly.
Do you guys agree with every part that Barry mentioned there? Assume it's a good 50 ohm barrel connector, good 50 ohm coax, yeah. I'm just adding 6 feet of coax. That's not much for 10 meters. So let's take a look again. The Smith chart shows kind of a figure 6 here. Now, granted, I'm 100 feet from the antenna. This is my Smith chart in my shack. Here's my SWR measured in my shack. I add 6 feet, and here's my new Smith chart. Oh, wait a minute, look. The figure 6 is now kind of a figure 9. So the impedance, as I measure it in my shack, the impedance has changed considerably. How about the SWR? No, look at that. It's the same graph. Let's go back. Here it is. Here's 6 more feet. No change. Well, hardly any change. Now, granted, if I add 1,000 feet, yeah, that would change it. So why is this? The SWR did not change by adding 6 feet, but the impedance did. Now watch out. The impedance, as I measured in my NanoVNA, I'm still in my shack. 6 feet, that's not much. Well, wait a minute. I'm on 10 meters. 10 meters. What's a quarter wavelength? I remember quarter wavelength on 10 meters is a little over 8 feet, because I remember those mobile antennas were about 8-foot whips. But that's 8 feet. And what have I got here? I've got coax. Good quality coax, but it's RG2 Thurn velocity factor of about 0.8. 0.8 of 8 feet. That's about 6 feet. Oh! So by adding 6 feet, what did I do? I added a quarter wavelength on 10 meters. Give or take a little. A quarter wavelength. Look what I did. Look at the Smith chart. Here it is, a figure 6. The closest is 0.3. The closest is still 0.3 to 0.4, pretty close. But I flipped this. My Smith chart has rotated 180 degrees. Whoa! So did my impedance change as I measure it in the shack? Absolutely. Why? Oh. Why does the impedance change by adding 6 feet of coax, but the SWR does not? So this is like the fundamental of the whole guts of what it taught me to get one of these NanoVNAs. What determines the SWR? Only one thing. Where the feed line meets the antenna, that determines the SWR. If that's reflecting, let's say, 30%, then that's reflecting all the way back, that 30%, all the way back to my transmitter or my antenna tuner or whatever I've got. The SWR is equally bad all along my coax, 3 to 1. But the impedance is changing every time I move. Why does the impedance change? Because the voltage, the current, the phase, they're all changing as you go up and down a feed line. Now, there's something magic about a half a wavelength. What's magic about the half wavelength? The impedance duplicates itself. A half wavelength on the Smith chart is rotating around, how far? 360 degrees. Oh, that's kind of weird. So a quarter wave of feed line rotates the Smith chart 180 degrees. That is so cool. I could not have explained that to you a year ago. So this NanoVNA has forced me to rethink transmission lines, coax. Now, this would not have happened if the SWR is 1 to 1. Why? Because then all the points would be right in the bullseye, and no real antenna does that. So let me stop. It's 3:40, and I've only gotten through about half the slides, but this is a good point maybe to stop and think about this. Let's say I have some feed line and some load, an antenna, and it plots here. This is just an arbitrary plot. And let's say instead of adding feed line, I cut some off. Either cut it off or add it. I don't care which we do, but in this case, what if I add 1/8 of a wavelength of whatever frequency I've got? At 1/8 of a can't get it. At 1/8 of a wavelength, this impedance point would plot over here. It's rotating around. Now be careful. It's not getting any closer to the bullseye. It's just moving around the bullseye. A quarter wavelength plots 180 degrees over. So I've moved 180 degrees, half a circle. 3/8 wavelength, and if this were my slide over here, if I add a half wavelength, I'm back to where, I lost my cursor, I'm back to where I started. There's something magic about a half a wavelength, 2 half wavelengths, 3 half wavelengths, 4 half wavelengths. The impedances duplicate themselves on a feed line, any feed line. Doesn't matter whether it's ladder line, 450 ohm window line, coax, they all behave the same, but they have different velocity factors. Let me stop here. That's pretty amazing. How about if I say it this way? Your feed line's part of your antenna. I know I've had people say, no, my feed line isn't radiating. Well, that may be true, but it's part of your antenna. Have I convinced you of that? The impedance is changing up and down the feed line.
Yeah.
Is the resonant frequency also changing up and down the feed line? Answer begins with a yes. 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 Yes.
But the SWR remains the same.
Yes.
Yeah.
So often we think, well, how can I improve the SWR? Could I improve the SWR by adding a little extra coax or cutting some off? No. No.
Unless the coax is part of is radiating, I suppose.
Oh, well, yeah, that's true. I'm assuming, you know, like the shield isn't part of the antenna. Yeah, yeah. Let me see what else I've got, but let me skip a couple. Okay, so here's where I think I probably confused it. In a way, I did it on purpose. Resonance. Let's think about what that word means. So I'm going to come back. This is my favorite analogy because I'm a grampy now. So I push my grandchild on the swing. You know, what's my job? I'm the feed line. This is an end-fed dipole. Do you see what I see? What's the kid on the swing? That's the antenna current on the dipole. When does a dipole radiate? Only when there's a current. So on an end-fed dipole, there isn't much current here. He's at rest. So where's most of the radiation on a half-wave dipole? Where the current's the greatest. Where's that? In the middle of the dipole, not at the ends. But the dipole is where Grampy is feeding this. Okay, so it's like an end-fed dipole. How does Grampy know when to push? What if I blindfold? I don't know when to push. Maybe my grandkid yells, "Push now, Grampy!" But she says to me, "Grampy, Grampy, push in phase with my natural period of swinging to increase my amplitude." Is she right? She probably wouldn't say it with those words, but is she right?
Yes.
Yes. How do we see this? We see this as the antenna and the feed line are in, what's the magic word?
In phase.
In phase or resonance. So at resonance, the phase, the voltage and current are in phase. Grampy is pushing, considering the kid on the swing. So resonance is strictly no reactance. The phase is correct. May or may not be a low SWR. Or not, they're not necessarily the same. So the input push from the feed line, that's Grampy. Grampy's push needs to be in phase with the natural vibrations of the current in the antenna. What determines that? One thing, the length of the antenna. Well, and maybe the proximity to ground and other wires, but that's the idea. So if your antenna has reactance, chances are it's either too long or too short. Does that make sense? Okay. So if Grampy pushes too soon, what happens? Well, that's happened to me. I don't pay attention and I push too soon. I crash into the kid. You know, it's like, crash, that's no good. I can knock her off the swing. What if I push too late? Well, that's equally bad. I'm running after her, trying to push. So this works best if what? Grampy pushes at the right time, in phase. Is that also true for your feed line and your antenna current? Yes. Yes. That's the ideal, but I'm not saying it won't work off resonance, but it works best. Why does it work best? Oh, it's a simple reason. You get the most current. Is that good? Yes, it's the current that radiates. Current, I'm talking about accelerated electrons. So resonance is important. But look, we all operate antennas off resonance, especially on 80 meters. So my antenna I can model, make it look like a simple RLC circuit. What's the R? Well, that's the resistance part of the antenna. What's the L? The inductance part. Well, wires have inductance. What's the C? The capacitance part of the antenna. Well, the charges are going out to the ends on the insulators. That's one giant capacitor. So my antenna can behave like this. But at resonance, the L and the C create an inductive reactance and a capacitive reactance that might cancel. Ah. So at resonance, the L and the C do what? Their AC resistances cancel one another because one makes Grampy push too soon, one makes Grampy push too late. So what will make, or what will allow Grampy to push in phase with the kid's swing? How can I get my feed line to maximize the radiation on my antenna? What can I do? If I'm operating off resonance, I may or may not have a problem. So this thing called impedance. What is impedance? My ninth graders would call it impedance just to get my goat. So impedance. What is it and how would you measure it? Well, my NanoVNA does measure it. Oh, okay. What is it? What is impedance? Well, it's a combination of the R and the X, isn't it? So what if my antenna is something that ends up as pretty close to 50 ohms, and my coax is 50 ohms, and my radio wants to see 50 ohms. Then I'm really happy. Everything looks like it's tuned up. It's in resonance. But if I operate on the low end of 80 meters or the high end of 80 meters, I know my SWR goes up, my radio might balk. What do you think's changing faster, the R or the X? The impedance is no longer 50 ohms because either the R or the X or both are changing. What do you suppose on an 80 meter dipole is changing faster, the R or the X? What do you think?
Let's say the X.
And why?
Don't know.
Pure guess. Pure guess. You got a 50-50 chance.
Yeah.
All right, well, here's a graph I pulled out of the W2DU, Walt Maxwell book, and I thought, this is just so cool. And then I highlighted it. So here's a typical 80-meter antenna. My antenna works pretty close to this. So I'm looking at this from 3.5 to 4 megahertz, 80 meters. Typical 80-meter dipole, close to the ground, so maybe the resistance is something like 50 ohms. Mine is a little bit lower and a resistance of about 30 ohms. But the resistance doesn't change much across the band, from about 52 ohms to 75 ohms. Well, it is changing. It's going up, but not too fast. How about the reactance? Well, let's look at resonance right here. Reactance is 0, right in the middle of the band, about 3.8 megahertz. So there's a typical dipole, cut to the middle of the band. What if I go to the low end of the band, 3.5 megahertz? The reactance is negative 125 ohms, negative. That's not very good. The reactance went from 0 at resonance to 125. The fact that it's negative just tells me, Grampy's pushing too soon. How about here at 4 megahertz? Well, wait a minute. Up here, the X sub L, the reactance is 100 ohms. So this definitely shows, if it's correct, the reactance is changing much, much faster than the resistance. So in order to correct this, what do I need to think in my shack? What do I want to make closer to the 50 ohm value? I want to change it so the reactance becomes 0. I want to cancel the reactance. Grampy, you're not pushing at the right time. Well, I can't literally, yell up to my antenna. So what can I do? What do I put in my shack that can cancel the reactance at the antenna?
I see.
An antenna tuner. So here's an example of an 80-meter dipole in a Smith chart. This is my 80-meter dipole. And it looks like at about position 2, 3.6 megahertz, it's got the lowest SWR. But look at the phone band, it's awful. The SWR is way up here, 3 to 1 or something. So I'm going to install an antenna tuner so I can make this antenna work on, a different band. I guess I included some other slides here. Oh, I threw some slides out. Okay, so what if my antenna was up here, let's just say? This isn't my 80-meter antenna. I need to move this impedance down to the bullseye. How do I do that? I do that with an antenna tuner in my shack. Or, well, I could maybe put the antenna tuner up at the antenna, but then I can't adjust it easily. It's, electronic or something. So we have these devices called antenna tuners with parallel or series inductors and capacitors. And I don't want to go into the gory mathematics here. It's kind of interesting, but with an antenna tuner, I can, going back to this, get rid of this reactance. And in my shack, but not at the antenna, in my shack, cancel the bad reactance so my radio never sees it. In other words, my radio thinks it's operating into a 50 ohm load. It's not. The antenna might be 150 ohm load with reactance, but my radio doesn't care. So what's my antenna tuner actually doing? It's sort of protecting my radio from seeing the bad stuff. Does that make sense? How does it do that? Let me jump ahead a couple. It does it by introducing another reactance. So if my antenna is capacitive, I throw in some inductive reactance, and this acts as a combination of two to bring the resistance back to 50 ohms. So the classic is something like this. If my antenna is, let's say, a long wire, and it's got a high resistance and a high reactance, coming into my antenna tuner, if I just have two parts, nothing more than that, you don't plug this in, a variable capacitor to ground, a variable coil. If I get just the right values on each of these, This brings the reactance to 0, and this brings the impedance back to 50 ohms. Well, that's kind of magic, but I need just the right values on this antenna at this frequency. If I'm operating, let's say, a short mobile whip, it still works, but the capacitor is on the other side. So this brings a low impedance. Step it up, bring it back to 50 ohms resistance. So in other words, this thing's called an L network. And you can basically hook up a single variable inductor, a single variable capacitor, in any one of these 4 combinations. And you have what's referred to as an L network. Why might I want one of these? Then I can match any antenna to any radio, almost. And it's really not that expensive. But I need to turn the dials until what? Till my radio's happy. You can build this for 10 bucks. You can buy them for a couple $100. You know? But they're basically the same thing. My Nano VNA, if I put it between the tuner, if I put the Nano VNA to the input of the tuner, then the tuner to the antenna, when I'm looking at the Nano VNA, I turn the dials on the tuner until when I look at the Nano VNA, the Smith chart, where's the cursor? In the bullseye. It's easy to do. How much power am I using in my Nano VNA to tune up my antenna? About a milliwatt. Am I going to QRM some net? No. I could use my radio, but then what often happens is I set my radio to 5 or 10 watts. I tune up on the net frequency, and everyone else is yelling, "You lid, move off the net frequency." You know, it always happens. I better stop sharing. I could easily go another hour. I'm not. There are a lot of parts to this Nano VNA that I had to learn how to interpret. It forced me to rethink Smith charts, impedance, SWR, return loss, all this stuff. It's a lot of stuff, a lot of content. And I realize I probably went too fast towards the end there, but I see it's almost 4 o'clock. So it's time to stop. Questions?
It's nearly 4 o'clock. It must be time for tea.
Yep.
Oh,
Very interesting.
interesting. Yeah.
I'm going to have to watch it over a couple of times to let it absorb, but I'm starting to get the gist of it now.
Took me 60 years. Was that recorded? Was this recorded, David?
Hopefully, yes.
Oh, okay. When I tried to play back the Nano VNA 1, for some reason when I clicked, view here.